Welcome back. In our previous section, we discussed about the different types of activation function. Now we'll see the interconnection of the neurons to form a fully connected neural network. As we can see from this figure, that this figure shows a generic architecture of the multi-layer neural network, and we can see multiple layers of neurons, which where each layer consists of a set of neurons in a column of the network. And if we see the zoomed uh, version of a particular neuron, uh, this like if we zoomed this zoomed node, this zoomed node shows a model of neuron, and it indicates that all the nodes in the neuron are artificial neurons of a form we described before, except for the input layer, where nodes are components of the input data X. We can see here in the layer 1, these nodes represents these nodes are nothing but the input data X, and we also see here that the output values are the activation value of the first layer are the values of the elements of X, and the outputs of other nodes are the activation values of the neurons in there. Like the outputs of all the other nodes are the activation values of the neurons in the particular layer, and each layer in the network can have a different number of neurons, but each node has a single output, and this output of every node is connected to the input of all the nodes in the next layer to form a fully connected neural network. And we also require there to be no loops in the network. Such networks are called the feed-forward networks. So in this kind of network, we don't have any kinds of loop or feedback loop, and there is no loop, and this is called the feed-forward network. And in neural network, we know that the input values of layer 1 or the first layer, we know the input values of the first layer, which is nothing but the data, input data, and we also can observe the values of the output neurons or the output. We can also see the output layer data. That means the we can see the activation output of the activation value of the output layer, and all other nodes or all other are hidden neurons, and the layers that contain the hidden neurons are called the hidden layers. Like we can see here we have got the layer 1, which is nothing but in the layer 1 it consists of the input data. This is the x1, x2 up to xn, which we know this value, and we also can observe the output layer, the data at the output layer, or the activation value of this particular node at the output layer. And beside these two layers, the data and the neuron, we don't know the are unknown or which are hidden, so these are called the hidden layers. Generally, we call the neural network with the single layer a shallow neural network, and we refer to the network with the 2 or more hidden layers a deep neural network. The neural network having a 2 or more hidden layers are known as the deep neural network. But this terminology is not the universal, and you can also see the words shallow and deep used subjectively to denote the networks with the few and with the many layers respectively. And as we have we can see here the lots of notations of the notation associated with this network. And since we have to account for the weights or parameters, inputs and outputs within the layer and layer to layer, we denote the weight of any connection by wij, as we have been using in our previous classes as well. And this connects the outputs of the neuron j to the input of the neuron I. Like we have got wij, which means it will connect the output of neuron j to the input of the neuron I. And as I said before, that the first subscript, which is I, it denotes the neuron that receives the signal, and the second subscript refers to the neuron that sends the signal. Like here, I receives the signal, and the second, which is J, that refers to the neuron that sends the signal. And for bias, we use the single subscript because for bias, it depends only on the neuron. So BI is the ith neuron in the given layer of the network. And the weight, bias, and activation function, this completely defines the neural network. Now we have to add another subscript, which is none other than L. This L is for the layers in the network. Here we can see, like we have got wij. This wij is for the weight, and we have got another subscript L. This L is nothing but the layer, and here it ranges from L is equal to 1 to 2. We can see here L, it will range from 1 to here layer L, 1 to L, and capital letter L. This small L gives us the this tells us the particular layer, and in the input it will be L is equal to 1. Its value will be 1 in the input layer, and it will be capital letter at the output layer. And the number of neurons in the L is denoted by NL, and which have two options to indicate layer and indexing the parameters of the neural network. And we can do this like we can also indicate, here we use this L. Actually it can be represented in different way, but like with the W subscript ij and superscript L. And another way is that we have used here W subscript ij and L, and this is most widely used, or it's conveniently used in most of the literature, so we prefer to use this one. And as we have seen that the objective of using a neural network is same as a perceptron, that is, we determine the class of membership or classify the unknown input patterns. And the most common way to perform the classification using the neural network is to assign as a class label to each output of the neuron, and thus the neural network with the NL outputs can classify an unknown pattern into the NL classes, into one of the NL classes, and the network assigns an unknown pattern vector X to class CK if the neuron K has the largest activation value. That means, suppose I have got this K and I have got different neurons, like here we can see we have got the output neurons, different nodes or the different output neuron, and if AKL is greater than AJL for J is equal to for while the J ranges from 1 to NL. This is the total number of neurons in the output layer, and J not equal to K. So that means we will assign a class to put this vector to the class if the output, the activation value of particular node or particular node is greater than all other nodes. Like we can see, suppose if the node value of this neuron is higher than others, then this input vector will be assigned the class of this particular output. And so let us see example with this using the forward fast through a feed-forward neural network. Here we will see some example, and the forward fast through the forward fast through a feed-forward neural network, it maps the input layer to the output layer, and the values at the output layer are used to determine the class of the input vector, as we have discussed before. And we will see how the feed-forward neural network carries out the computation that results in its output. And for simplification, we assume that the network parameters are none. Like here, we assume we already have the non-parameters, or we know the weights of the network. So we have a very simple example here. Before we compute, like we can see here, like in our network, the outputs of the layer 1 are the components of the vector x. We can see here, like in the layer 1, here in the layer 1, the components of this layer are the input vectors, and it will be the output of this layer, like the output of this layer 1 is the component of this input vector, that is x1 to xn. And what we do is we compute, the computation is performed by neuron I at layer I is, like here we compute, like the neuron computes, the neuron performs a computation which is nothing but the weighted summation of the input, and the input is this input will be the output of the activation value of the previous layer. We can see here in the diagram that suppose for this second layer, for the layer 2, the layer 2 will have the input which is the output of activation value of this previous layer, or we can see here at the AIL, the output of this, the input of this neuron will be the output of the previous activation, or we can see at this which is same in this layer L as well. And we just take this weighted sum of the input, weighted sum of the weight and the input values plus the bias, and here ZL is called the net or total input to the neuron I from the layer L. And after we get this net input, we estimate the activation function, we fed it to the activation function, and we get the activation value. And here H is the activation function, and the value of the network output I is given by this AIL is the output. It is the output layer, and this L indicates the output layer, and the value of this network will be the first we estimate this net input, and then we perform the we feed it to the activation function, or we get the activation value from this function. And let us see a simple example for this activation function. Here also, as I have said before, we assume the weights, and here is a simple numerical example. And this figure shows a 3-layer neural network, and it consists of input layer, one hidden layer, and one output layer. You can see here, this is the input layer, one hidden layer, and one output layer. And the network has it accepts 3 inputs. It has accepts 3, this x1, x2, x3. It has 3 inputs, and it has 2 outputs. Thus, the network is capable of classifying 3D patterns into one of the 2 classes. And the numbers shown above the arrowheads on each input to the node are the weights of that node associated with the outputs from the nodes to the processing layer, like this 0.1, 0.2, 0.4, and 0.6, 0.4, 0.3. This represents the this represents nothing but the weight or the parameter values, and the number, and similarly the number shown in the output of each node is the activation value A, like we can see here. This 301, this is the activation value for first layer node in the first layer, and 0.758, 0.8176, these are the activation value for this node, and 0.6982, these are the activation value for the nodes at the layer 2. And the inputs associated with the first layer with the ones are bias values, like we can see here 111. We just assume we put this 11 as a bias value. Now let's see the computation performed at each node, starting with the first top. We can see here at the first top in the layer 2, like we compute the net input Z1 here, Z1 2. This 2 represents the layer, and this Z1 represents the net input, and we compute it with using this weighted the summation, like we multiply the each input values with the activation values with the weight, and then sum it and add the bias value, which means that we perform the weighted sum and get this net input value. Then we use sigmoid function to perform the activation. We use sigmoid function as activation function and gets the output of this activation, which is 0.7858 for this particular node. Similarly, for the node 2 in the layer 2, we estimate the net input to the neuron and the activation value here, which is 0.817. And then in the output node or the layer 3, we estimate the output. First we estimate the net input and similarly we estimate the this similarly we estimate the node output of the neuron on the first node, and the output of the output value of the second node or second neuron. And now this is the output at the activation value at the activation value at the neurons in the output layer will tell us which class does this input belongs to, and we will compare, or we'll compare the output values, and then based on that output value we will decide which class it belongs to. Like if we are using the network to classify the input, we should say that pattern X belongs to class C1s. This class C1 means the first class if A1L is greater than A2L, where L is 3, like this is the third layer, and NL, the number of nodes in the output layer, is 2. Here, if we can see here that the output value of this node is greater than this node, or the first node is the value of the first output value of the first node is greater than the output value of node 2. So we say that this input vector belongs to the class, this class. And